Thank you to you for inviting me today, and it's a pleasure to present what we can do with machine learning, artificial intelligence to help the supply chain perform better. So I'm going to present Vekia, but before I do that, I wanted to say a few words about myself. So I come from the academic research. I did a PhD in France in machine learning, and then I came to the UK and I started a machine learning activity in Cambridge University. And I came back to CNRS and INRIA in the early 2000s, and I created Vekia about 9 years ago now. So before I explain what we do in scientific terms, I wanted to explain why we do it, and because there is a big need in optimizing the supply chain today. So in a few words, supply chain companies, and this includes retail companies, logistics companies, and most industrial companies, they need to be able to deliver one product at a given place, at a given time, chosen among millions on a very wide variety of locations and all over the world. And this is a very complex problem, and we will see why later. And so the need is to implement a global, agile, and supply chain. Each of these words is very important. Global, because we have global customers on a global scale. Agile, because business is changing and renewing itself very fast. And efficient, because they want to make money. So if we look at this technology in a few slides, we have three main know-how. The first one is in the data collection and management. This is a classical know-how, and in this case, it is on a very large scale, and I will give you figures later, where we take all the data that are somehow related to the supply chain. So we need to have description of the locations, including the stores, e-commerce sites, warehouses, distribution centers. We take all the information we can about the products that are going to be delivered. So we take the structured information, but also the non-structured information about the product. The third point is to look at marketing. Is there a promotion, an advertisement, or anything that can change the demand? We look at what's called the merchandising, the way the products are presented in the stores or in the warehouse, in the website. And also we look at the logistics network, where are the locations, where are the stores, and how are the products transported from one place to another. So this is the first bit of technology. The second piece concerns demand forecasting. So it is a very old and classical problem, but it can be renewed by machine learning, and it has to be renewed because the objective we now are faced with is now much more high than it used to be. So for several reasons. The first one is much more products and much more sites. So every day we need to compute sales forecasts for tens of thousands of stores and for hundreds of thousands, even millions of products. And we do it because it is a forecast for several time steps. So we very easily achieve several billions of sales forecast values to be computed every day. So this is the first challenge. And the first challenge is to be able to have coherent sales forecasts between the stores, the warehouses, and the suppliers at different time scales. And the third bit of technology consists of computing the stock transportation that needs to be done from one place to another. So we compute delivery orders, orders from stores to suppliers, and stuff like that. The objective behind that is to be able to have the shortest possible delay, the lowest cost, and the widest geographic coverage. So I will be fast on that, but our customers, they need that because it helps them make more money. But much more than that, for some of them, it is a question of survival. If a retail company, for example, today is not able to deliver fast its goods and with a low price, you don't buy to them. If you buy today on the e-commerce sites, you want to have the product in the few hours at maximum and not in 1 month. And so there is a rise, there is an automation. So this kind of technologies, they quite automate the way the stock is managed. We replace armies of people with Excel files, putting dumb figures in Excel sheets, which are almost 1 million lines long, by a fully automated computation, as I change from this kind of business to supervising the replenishment. It is agile and it is robust because it works for several years already. This is our geographic coverage. So we manage stock today in 70 countries. Some of our customers, and the list is growing very fast because we are at the heart of their operations, and we can have an impact of up to 1 billion euros in working capital for big industrial companies. So let's go to the core topic of this presentation. First, I will be starting with a concept that is really much used, which is big data, and I wanted to explain its meaning in terms of supply chain. First point is, so you know the presentation by the 6 V's of big data? It is a very classical definition. So the first one is, of course, when we speak about big data, we think about volume. So I gave in this example 1 billion sales forecast to be computed every day. But we have also the issue of visualization. When you have such a big amount of data, how do you look at it? So this is also a very key point. This is an example of screen that we're doing to represent the data. In this case, each square is a store with a specific value attached to it. Velocity. When you compute replenishment on a regular daily basis, if your computation takes more than 24 hours, then you have a problem, of course. So you need to compute very fast. You have the problem of variety, because data are structured, non-structured. You have colors, you have geographic locations, and we'll be talking about it later. You have level of fashion. What does this mean? And you have also a problem of veracity. Most of the data is wrong because the stock, the inventory, you have all experienced that. You go to a store and you ask if they have more product in the back of the store. They say, yes, we have it. And then the manager comes back and said, I'm sorry, we didn't have it effectively. And this is all the time there are discrepancies in the stock data. And also recently I found in the database this color frog pink. So this is an example of mistakes. And this data has a lot of value because it brings a lot of added money for our customers. So this is typically a big data problem. So now if we look at artificial intelligence, I have proposed here a definition of artificial intelligence because we hear a lot of this word and sometimes we don't really know what we're talking about. So artificial intelligence is the ability exhibited by a machine to perform a complex intellectual task that was previously devoted to a human. You know of all these examples, and there is a big change between the first one and maybe two and the last ones in the examples. And the change is machine learning. The first ones were programmed fully to achieve, for example, chess game, it was fully programmed by humans. It didn't learn anything. But now if we go to the Go game, it has a lot of learning inside. It learns from past games that have been done previously. So machine learning, it is a scientific field that aims at giving artificial intelligence to a server. And how does it work? It works by learning from data. And today we have a lot of machine learning algorithms available to complete complex tasks, but these tasks are still very specialized today. Examples are image interpretation, speech recognition, we can also predict consumer purchase, and this is what we do, forecast the sales, for example. These are examples of machine learning. You know that it can be supervised, that is based on example, or unsupervised, that is based on discovery, or reward, if we talk about reinforcement learning. So these are examples, you can go through it in Wikipedia or other sources. And what's not always understood is that machine learning can be batch. You can learn once and use what you've learned all over again, and you don't need to renew your knowledge, but it can also be sequential. That is, you update your learning every time you get a new data. And of course, it requires a lot of computation power and data, and this is one of the most important reasons why machine learning was not so developed before. I wanted just to emphasize on the point. I sometimes hear or read in the press that there have not been any progresses in the algorithms over the 30 last years. This is not fully true. There have been really big advances in the research as well. So machine learning is a very active research field. So what is machine learning? If we look at supervised machine learning, you have examples. I will be doing a little bit of math here. Sorry for that. So you have examples X, Y. X is the data and Y is the value you want to predict. What is machine learning? It is you want to learn a function to transform this data X into what you want to predict, which is this value Y. So this is nothing but learning a function. And this is the outcome of a machine learning algorithm. I try to make it as simple as I can. Sorry for this one. But the way you choose f, I will try to explain it with words. The way you choose your function is that first you want it to fit your data in the training set. So these examples, x, y, x and y, you want the function to be good on the past observations to predict the value. So you verify in the past that you can actually very well forecast. And this other term is really the key point in machine learning, because this omega of f is a function that measures the complexity of f. So it's a bit theoretical, but there are many ways to measure the complexity of a function. And what this says is that the optimal function you want to find with machine learning is the one that is good at predicting the past, but also which is simple enough. And this is really the key point. And all the machine learning algorithms that I have listed here, they all, in a way, implement this idea. So if you apply that to sales forecasting, you will be using your past data, past sales, past context. I mean in that it can be weather forecast, the past weather, sorry. It can be also the past promotions and the past exogenous data, such as calendar day or was there a school holiday at that time, etc. You put that into the machine learning algorithm and you end up with what you look for. It is a function. And from this function, not only you have learned something, but you can also have a different view of the past, because you can remove the effect of promotions in the past, for example, to look at what the sales would have been if you didn't have a promotion. And this is a very important information to have for retailers, because sometimes it says that the sales would have been the same, more or less. So you just spared useless money by implementing this promotion. This is what we call demand sensing. And another thing we can do with these functions that we've learned is that we can use it to forecast the future. So you put into this function what you know about the future. You know that there will be school holidays from July 7, I think, to August, I don't know when is the end of the school holidays. You know that you are going to implement a commercial promotion, and you know that you are going to have, maybe in some cases, this kind of weather or another, and you can use this to forecast the demand. But you can also change the parameters of the commercial operations to have an optimization of the promotion you are going to implement. So you can also use it to tune your parameters and to upgrade the quality of what you're doing on a daily basis. I have made here a focus on the forecasting of new product. So this is a very important problem for industrials and retailers. It is to decide how much am I going to sell of this new product. Very hard question. There are no way to find the exact answer, but there are many ways to have a much better forecast. And this is one of them. In a simplified way, you can see it as this. Here you have the sales curves of many products over the weeks. So this is a period of 10 weeks. And by using, for example, a clustering algorithm, you can separate the behavior, the sales behavior of these different products. Actually, it's a bit more complex than that, but I simplified it this way. So you have groups of products with the same behavior. These are products who already exist. So you are not yet with the new product. And the next step is to learn from these groups what are the statistical representation of the characteristics of the product in each group. And for example, you will see here, and it is a real example, you will see in the first one, for example, for men's fashion retail, you will see the suits, the white shirts, the ties, and stuff like that in the same group, which is obvious for everyone, but in retail organization, it's managed by different people. So they use different curves. So you can characterize each group by its features, and you build what you can see as a decision tree. This decision tree says, if the color is this, then it is more this group. If the price is this, it is more this group. And when you have a new product you've never sold before, you start from these characteristics, and you apply your decision tree, and you end up with a forecast curve. And this kind of method, although presented in a very simplified way here, is very, very powerful. And it increases really the sales forecast of new products a lot. Another problem that we can solve in the supply chain with machine learning is that of coherence of demand forecast all over the layers. Because you can easily, or not easily, but you can build a forecasting algorithm for the stores. So you have a forecast for each product in each store every day. So you're very happy with that, but then you say, well, I need also to replenish my distribution center. So I need to have a forecast for the distribution center. So how am I going to build this forecast? If you sum up the forecast of the stores and put it up at the distribution center, you will have a lot of variance. You will have a low bias, but you will have a lot of variance. So this is not accurate. And the more you go up in the supply chain, the less accurate the forecast. So you could say, well, I'm going to do it the other way. I will forecast at the layer of the provider, and then I will divide my sales for each site, and then I will divide it for each store. But if you do that, you have a lot of bias, and it is not good as well. So you have this problem of having good forecast at all the levels, and you need to have this vertical coherence. What does this mean? If I make a promotion on these stores, I want to see the impact of the promotion in the sales of the supplier at the upper level. So this needs to go up and down. And at the same time, I have this local accuracy. So what we do with machine learning is to learn forecasting function at each of the layers. And we also learn functions to model the relationship between the layers. And this is how we have a very good accuracy everywhere, and how we have good coherence everywhere. This figure is quite shocking for users, but it's true. The computer is more efficient than human replenishment in 95% of the cases. And we have experienced this in 3 different contexts, and we've always found this figure. So which means that only 5 out of 100 people are doing better than the computer on a regular basis to compute the stock and to buy it with their suppliers and to replenish the stores. And another very big and important figure is that if you automate this process, not only you will increase the quality, but you can spare up to 100 man day in stores. And this is what we've done with our customers. And these are not days that are lost, but they are used to manage the team, to look at the customers, and to work with the suppliers. So 2 use cases of machine learning in supply chain. The first one is retail. I have been speaking a little bit about retail already, but you all have a smartphone, I guess. So you all buy and compare prices between various vendors. So you have a new expectation. We have a new expectation, and retailers need to adapt to this expectation in terms of delay, in terms of choice, and in terms of price. And there are new ways to buy, click and collect, ship from store, stuff like that. So retailers, they need to be able to forecast where they will be selling a given product on a very precise location and a very precise time. And this is why they tend to do more and more sales forecasting to steer the replenishment and stock management. Another example is in industry. We're working, for example, with car manufacturers, and one of their point is to have the lowest working capital and to fight depreciation of the products they've manufactured, because they don't want to have them forever in their warehouses. So they need to product and ship exactly what's necessary to achieve their target KPIs. And this is a very important statistics here made by Gartner. And it shows that if you increase the sales forecast by 1%, for example, you reduce by almost 4% the time to deliver one product to a final customer. So when you increase it by 10%, it really makes an asset in terms of efficiency. So just to explain what we do, we have observed that with machine learning we can increase the forecast accuracy by 10%, which is just huge, because some industrial companies have invested tens of millions of euros and maybe 30 years to gain 5%. So it's just a big step. It really changes the way they are working. So some concluding remarks about supply chain and machine learning. Supply chain is at the core of industry. It is full of big data, and not applying machine learning to it is really a waste, because it is very efficient and the supply chain becomes anyway much too complex to be managed by humans. So artificial intelligence is very good at that, and machine learning is the way to implement machine learning, artificial intelligence. And that's also my last slide.
Okay, Manuel, thanks a lot. Please join me there. So we have a few time left for a Q&A. I'm just going to start, and then you have time to think about your first questions. But coming back to your point regarding accuracy, which is always the issue, how long does it take to get the right accuracy at the algorithm level, and how much data do you need to do that? Because what I heard also is it's good to have the right algorithm, but you have to make sure that it's learning from the right set of data. So can you just describe the process there, and how long did it take you to achieve that?
Many years, a few years, I would say. Yes, the data question is the key question. And most industrials say to us, we cannot use your solution because our data is not good. And I say to them, well, you're just like everyone. So data is never good, it's never perfect. So what we have done is that we have identified, it's just like an onion. You have the core, the center, and you have layers of additional data that you can be using. And each time you add a layer of data, you increase the sales forecast. And at some point, if you add more data, you are only adding noise. So we have a good know-how on the way to identify which data are really to use and which ones are not to use. And so we have developed specific versions of our algorithms to both learn and identify if a data is positive or negative in terms of better forecast accuracy.
And there is no private issue. I mean, with the when you're working with retailers, you have many competitors in the same sector. You're using the data of all these different competitors to improve the algorithm, and so you learn from one retailer to make the other one better, maybe in terms of solution and stock replenishment. And so how do you manage that? I mean, how do you manage the privacy coming from different retailers in the same industry? And do they ask you for that, or do they accept the fact that the more they share, the better they're going to get from your solution?
What we see is that it's very difficult for them to accept to share data and to mix them with other retailers' data. So today we are not able to use the data of everyone to make a forecast for one. But what we do, and they know we do that, is that we train our system on each of the databases, and we optimize the meta parameters at a higher level. So we have a larger set of data, and when you engage a new customer in this vertical, we have already well-tuned algorithms, and it is also good for them because it's more accurate.
But what you're saying is it's specific vertical by vertical. For example, if you go to the automotive industry, the car manufacturer, you're going to use different algorithm or different assumptions than when you work with other retailers. That's what you're saying?
No, it's the same core set of algorithms, but the parameters that we have tuned is not exactly the same.
Okay. I have a lot of other questions for myself, but any question from the room? There's one over there.
A question, what's your relationship with your client? Is this sold as a SaaS? I should know this if I looked at the website, which I haven't done, but what's your commercial relationship with your client? And is it, and how are you billing them?
Well, we are a SaaS solution first, and we know that switching from a previous generation solution to our solution is a big step for them. So we do that step by step, and usually we let them try us for a few months. And we implement first data connections, and we start implementing the system, and then we look with our customers to the results we have. And once they are our customers, we have, like many companies, account managers who take care of them.
Yeah, there's a question on the back, Alexandra, over there.
Yeah, hi. Whom does your model belong to? Like, is it to your clients? Is it yours? Where is it hosted? Also,
It's ours. It's hosted on our servers. So all the IP is ours. Yes.
cool.
Just wanted to know in terms of users, who are the typical users? Are they product managers? Are they category managers? What are the kind of users you have?
Yes, that's a very key question. We have those you listed, category managers, product managers, and we have replenishment managers. We have, for some of the functionalities, logistics managers, warehouse managers, and people in the stores or sites who are local replenishment managers. But usually we interact with the big populations through the ERP, because we connect our data to the ERP in and out. And for some of our customers, they don't even know we're here, because they just look at the ERP screens and they have no idea that there is Vekia behind.
Getting maybe a bit more technical, you talked a lot about data coming from the company. Do you use also, I don't know, other kind of data, macroeconomics or whatever?
Yes, there are two kinds of data. Those who are provided to us by our customer, its own proprietary data. And on top of that, we have agreements with other companies to provide with weather data in the past and forecast, and also data collected from the social networks, from the internet in general, from the product advertisement plan, for example. So this is really one of the key points in achieving high forecast quality, is to use this kind of data. It depends. Some of it is free, and for some of them we need to purchase it in the name of our customer.
How do you deal with unstructured data?
So the question is, let me repeat it. So how do you deal with unstructured data? And more generally, I had the same question, because you said most of the data is not clean.
Yes.
When you're working with retailers and they don't have the reputation to have clean data. So how do you work with unstructured and not clean data?
Okay, so two different answers. For unstructured data, we started very simply by counting words, for example, and it's word statistics, and then we entered in the world of semantic analysis, so we don't do it ourselves. For this kind of thing, we implement toolboxes. But we have found that there is a lot of key information in the way product managers describe their product. And this is much more important to have this information than the structured data. So this is a kind of answer for that. And about the fact that the data is erroneous, the key point is to build models that do not rely on the idea that the data is exact, but which include noise, as we say scientifically. because there is noise.
Okay, last question, or we move to Miguel. Last one, Alexandra, up there.
Hi, have you made your own algorithm, or are they mostly built on like open source algorithm, and you have made some change to them, and do you commit again?
Can you put it the micro?
Okay.
Please.
Have you made your own algorithm, or have you used some open source algorithm, some all known algorithm to all of us, and you made some change to them? And do you commit them back to the? What's your relation to the open source world?
Yeah, we have all of our algorithms are proprietary. We started very early in the first stage of the company to build everything from scratch. Then, for some reasons, we switched to toolboxes with open source code, and now again we go back to our own developments, because if you want to achieve the highest forecast accuracy, you need to change the classical algorithms, because we need to put into them some layers of generative models, and if you don't tailor it yourself, it doesn't work.
Okay, Manuel, thank you very much. Thanks a lot. Wish you all the best.